So one of the key components of the college's undergraduate education experience is research. And we are committed to advancing knowledge by providing progressive undergraduate research opportunities, whether it's developing research plans, writing proposals, conducting research, analyzing data, or presenting research results. These opportunities provide students with a deep understanding in a scientific area while gaining hands-on experience. Undergraduate research is a great way for students to learn from faculty, researchers, graduate students, and other undergraduate students who share similar career interests or goals. Simply put, being involved in research greatly enhances a student's degree while providing them with the experience needed to make them competitive for graduate school or science careers. Recognizing the value of having these students communicate their research and campus experiences so that anyone can understand what it's like to be a student at MSU today, the college established the Dean's Research Scholars Program in 2012. The Dean's Research Scholars personify the high caliber of the college's student body and exemplify the traits of true Spartans. And we were honored to have these students represent Nat Sci this past year at events and speaking engagements. To help give us a glimpse into his undergraduate research, here is physics senior Kay Dembski.
Hey everyone, thank you so much for having me. Really happy to be here and share a little bit of what I've done over the last couple of years with you. So I, as Dr. Wilson mentioned, am a senior in physics, so I'll be graduating in 2 weeks. A little scary, but I was born and raised in East Lansing. I was born actually at Sparrow Hospital, just down Michigan Avenue. I've been here my whole life, and next year I will be pursuing a PhD in physics at the University of Notre Dame. But today I want to talk about what I've done while I was here at Michigan State at the National Superconducting Cyclotron Laboratory, big nuclear physics lab on campus, soon to become the facility for rare isotope beams. Actually, I believe that's happening right now. The first public ceremony for FRIB is going on. But to start with my work, I want to look at something that's pretty familiar to all of us, and that's the periodic table. So this is one of the most recognizable symbols of modern science. And I think it's particularly, it's so universal because it's really, really useful. It's a very creative way of organizing all of the elements by common properties. And it really allows us to make a lot of, draw a lot of information about them based on their relationships. And so they're all organized into these boxes based on the number of protons that they have. So, 1 all the way at the top left, going to 2, 3, 4, number of protons. So in nuclear physics, however, one of the things we're most interested in is different isotopes. And so different isotopes of the same element have the same number of protons, but a differing number of neutrons. And so differing numbers of neutrons can give all sorts of interesting exotic properties to these different nuclei. And that doesn't really come across on the periodic table because we just group them based on protons. So in nuclear physics, we often look at this giant structure called the chart of nuclides. So in this, all of these boxes on the periodic table are expanded into a whole row in this chart of nuclides. And so the protons increase as we go up, and the neutrons increase as we go to the right, and we get this big diagonal structure with a lot of boxes. So there are a lot of nuclei that we know and understand how to produce and study. And we, as nuclear physicists, and particularly as experimental nuclear physicists, are really interested in measuring as many properties of these different nuclei as we can. And so, as I mentioned, I work here at the Facility for Rare Isotope Beams, or National Superconducting Cyclotron Laboratory. And this is a very, very large facility that's dedicated solely to measuring all of these, producing these nuclei and measuring their properties. And so that begs the question, why do we do all of this? Why do we produce these rare isotopes that exist for, as few as a couple of microseconds, just to study all their, their mass, half-life, things like that. And so some of the big applications of nuclear physics that you may not think of are materials science, astrophysics, which is the area that my group's most interested in, nuclear medicine, which is one of the most interesting to me, things like brachytherapy, proton therapy, nuclear physics and medicine often can seem kind of at polar opposite ends of the spectrum, but there are a lot of very interesting applications of rare radioactive isotopes in medical research. And then, of course, things like nuclear power, as well as a couple other things in archaeology, like radiocarbon dating and techniques like that. So from here, I want to talk a little bit more about the astrophysics side of things and talk about my group specifically, because we're interested in something called the neutron capture cross-section for various rare nuclei, which is essentially a measure of how likely a nucleus is to absorb neutrons from its environment. So this changes the isotope, but not the element, right? We're increasing the number of neutrons, but not the number of protons. And so this is very relevant in astrophysical scenarios like supernova, where there are a lot of neutrons around. And so the way that my group in particular tries to measure this quantity is by looking at these things called Oslo matrices. They're these really colorful triangles that we kind of are specialists in looking at. And if it's not incredibly obvious to you how this energy graph becomes a neutron capture cross section, that's okay, because it's not really obvious to us either. The analysis for these matrices is a pretty complicated statistical process that has a lot of uncertainty associated with it. And so we're very interested in, well, essentially automating that because these things do have consistent patterns that show up that are much easier for a machine to recognize than they are for us. So kind of the end goal of my project, the dream, is that we can take these pictures, put them through a machine learning model. It does all the work for us, spits the answer out, and we're done with our analysis. And of course, that is a little bit of a pipe dream, but that is the goal. So how is this going to work? Or to phrase it a little differently, how do machines learn? And I want to show you that it's not so much like this, but a little bit more like this, which you can argue is a little bit more boring. Aside, I did not think that this was going to be the third picture of Arnold Schwarzenegger shown today. So I think one of the best ways to illustrate this is with an example. And one of the classic machine learning examples is basic classification. So let's say I wanted to train a model to recognize pictures of cats versus pictures of dogs. So I'll give it a picture and it has to tell me what it is. So the process that we would take to try to teach a machine this is kind of similar to how we would do it for a human, but a little bit more mathematically. So first step is I will feed this picture through the model. This is where the math comes in. It does a bunch of fancy math, and it either gives me back a 0, saying it thinks it's a cat, or a 1, which thinks it's a dog. So if it's right, that's great, but it usually won't be, because at this point, it's essentially just doing random math to the picture and either getting a 0 or a 1 out. So it's not going to have any consistent correct or incorrect answers. And so we got to make changes to make its decision more informed, essentially. We have to change how it does this math to get the right answer more often. And so that algorithm is called backpropagation. It's a mix of statistics and calculus that's very interesting, but very unwieldy. And there have been a lot of great work that's been done in optimizing it, so we don't have to do it ourselves, but it's a very, very cool algorithm. So then we rinse and repeat thousands and thousands of times with thousands and thousands of different images. And finally, we reserve some data, new data that it's never seen before, to test it on and make sure that it's doing the right thing. So if you look at stage 1, stage 2, a little bit of stage 3, this is kind of like teaching a toddler to recognize things. I'm sure any of you that have had kids know that kids ask what things are all the time, and they aren't always correct in their labeling of things. So you have to teach your toddler, this is the family cat, this is the family dog, and they'll probably mix it up for a while. And so rinse and repeat until finally, through trial and error, we get kind of a generalized picture of what things are. So this is a great simple example of how kind of the general machine learning process works and for a classification problem. So that is where there's a discrete number of outputs, either in this case, cat or a dog. For problems that don't have those set categories, we have to work a little bit differently. So in that case, we don't really tell it right or wrong when we want it to adjust what it's doing. We give it kind of a hot to cold scale. So if it's doing really, really well, we say, oh, that's hot. You don't need to make a ton of changes. It's not doing as well, doing a little colder. So that's what we have to use for my project in particular, because we're taking those triangle graphs and we want to get at the very, very end of the process, essentially a number out. So this begs the question, if the machine does all of the learning, what exactly do I do all day? And at the beginning, I wasn't sure exactly what I'd be doing all day either, because I too thought the machine would be doing everything, but that's not true. So one of the main things I have to do is generate simulated data. So I said we have to show it thousands and thousands of images of whatever we want it to learn. So either thousands of pictures of cats and thousands of pictures of dogs, or in my case, well, tens of thousands of those triangle graphs that I showed you. And so after I generate all that data, I feed it through the model. I tell it, okay, this was right, this was wrong, this was okay, this wasn't. It makes all this changes. I have to go through and then feed through all that testing data. Essentially, I proctor an exam for it, and I give I grade it, give it a score, see how it did, and then I have to make changes if it wasn't good enough. So then that's kind of the long, overarching goal of this project, and overarching role that I have is in the project is decide what the best combination of, structure for the program, how we format the data, and the specifics of how it learns. And we have to try to optimize that to have it learn a pretty complex problem as best as possible. And so a little more recently than this presentation, I've picked up a couple other roles. We've had some pretty good success training it on fairly simple Oslo matrices. And so we're actually writing a paper on it right now. So I've been doing a lot of writing, generating figures, making pretty pictures. And then also, as I'm graduating in 2 weeks, I've been training a new student to take over the project after I'm gone. So we don't have a lot of people in my group who know a lot about machine learning. And I actually came in and learned a lot of this from the ground up, which is why it's been such a long project. But I'm excited to kind of pass this along to the next generation after this and see what we can do, maybe 5 or 10 years from now with it. So with that, I thank you for listening.